Hi, and welcome to Module 6 in Video Lecture 2. This is the second and longer module on relations, and it relates to properties of relations, some stuff you can do with relations, and the utility representation, but here only the single relation, at least as good as. If you recall from last module, at least as good as is written like this. This is to be read A as at least as good as B. There are also variants A is strictly better than B, and A and B are different between A and B. Some characteristics of these we need to do first. The most basic characteristic is completeness. Let's say I have a set of elements that are of some interest to me, and I want to know how to choose one from that set that I like best. Well, the very minimal requirement that I must have over my preferences is that I must be able to distinguish between each pair of those items. If I can't tell you which one I like better. So completeness says for every element A and B, that's for all again, for all elements A and B in some set of objects, either A is at least as good as B, or B is at least as good as A. That means I must be able to order, in this weak fashion, all elements in my set, otherwise I don't have complete preferences. And complete preferences are assumed by, as far as I know, pretty much every model in political science or social science in general, because if you don't have complete preferences, the question of what you want is just unclear. Right. Now that said, it's possible that you can violate this assumption if you truly don't know, if you're given two options, you just truly can't decide between them at all. Right? Not because you're indifferent, but because you just can't actually compare them in some fashion, then this is violated. But indifference is fine, preference is fine. You just can't you can't have the situation in which you have no idea how to compare two things. We assume we can always compare two things. Completeness is almost always assumed. Another property that's commonly used is reflexive. Reflexive is an odd one. For all elements in your set, an element is at least as good as itself. You might think it's kind of pointless, and in a sense it is. It's kind of akin to saying 3 is greater than or equal to 3. That's true, but uninteresting. But it's an important property nonetheless that we generally assume is true. The third property that's so popular that it's entered the sort of general lexicon of things that get thrown around in pop culture is transitivity. You might hear by the transitive property. Transitivity means for all elements A, B, and C in X, if A is at least as good as B and B is at least as good as C, then A is at least as good as C. This can also be violated, right? So let's say I like apples better than oranges, and I like oranges better than bananas, but bananas better than apples. Well, that violates this transitivity, right? Because if I like apples better than bananas and bananas better than carrots, say, then I should like apples better than carrots. But if I don't like but if I like carrots better, then I violate transitivity. People in real life do violate transitivity. However, we would generally assume that transitivity is also satisfied by all people's preferences. Why? The reason, one reason is the so-called money pump. Let's say I give you a choice. Let's say you have a banana. Let's say you have a carrot to start off with. You have a carrot. I give you a banana for your carrot plus a penny. You say, sure. Then you have a banana. Now I say, I give you an apple for your banana plus a penny. You say, sure, the apple's better. Now I have 2 pennies and an apple. What if, instead, you strictly preferred a carrot to an apple? Then I said, okay, I'll give you the carrot for the apple and a penny. And you say, sure. Now you have a carrot and you're down 3 pennies. Now, these are R's, so strictly speaking, you might be willing to trade without a penny. That's fine. You're still at least down at least 1 penny. Every time we do the cycle, you lose another penny, and eventually I can take all your money. Right? That's the money pit. Money pump. So transitivity is generally assumed because the assumption is that if we aren't transitive, then we'll lose all our money. We can be taken advantage of by clever and rude economists or whatever. But nonetheless, we assume transitivity because the reason is transitivity is sufficient, but not necessary, to obtain an actual best outcome for yourself. And the reason relates to that example. Let's say you actually have A is at least as good as B. Sorry, let me read this better. A is at least as good as B, and B is at least as good as C. But let's say C is better than A. Well, what if I'm trying to decide what to do? Well, okay, I have A, B, and C to choose from. I'll choose A. Oh, but wait, I like C better, so now I'll choose C. Oh, but wait, I like B better, so I'll choose B, and on forever. I have a cycle. This set of preferences, with strict preferences in them, is known as a Condorcet triple. Condorcet, mathematician, did a lot of stuff, name will pop up a lot. This is a Condorcet triple, or Condorcet cycle. And it occurs when the decision, and this is usually in the context of a group decision, not an individual decision, but it doesn't matter for this example. It occurs when a decision cannot be made because you cycle endlessly through a series of 3 or more options. So transitivity avoids that. Transitivity also avoids allows you to do something important, which is to represent preferences as utilities. Utilities are particular functions that map some set of stuff to the real line, so they provide numbers. They assign each individual object a number, and by comparing the magnitude of numbers, you can determine what you like better. So if I have preferences like A is better than B is better than C, my utility might be 3 for A and 2 for B and 1 for C. And that would give me 3 is better than 2, which means A is better than B, which is true, and 2 is better than 1, so B is better than C, which is true, and then I'm done. Note that for numbers are transitive, so 3 is better than 1. I can't have C be better than A if I'm assigning numbers to them. Therefore, my preferences must be transitive if I want to assign utility functions to my preferences. Why might I want to do that? Because it's a lot easier to work with utilities that I can manipulate these functions, differentiate them, optimize them, than it is to figure out the optimal choice if all I have is a list of relations. So it's a lot of times much easier to understand what my best choice is when I have a choice in the context of a utility function than when I have the choice in the context of a bunch of relations. So utility functions can be very useful, and we'll deal more with them when we deal with optimization in part 2 of the class. Condorcet triples make it impossible to have a utility function for yourself. Okay. Before moving on, there's one other property you might see occasionally. If something's symmetric, then if A is at least as good as B, B is at least as good as A, this is not required by any theory. Just if you have a symmetric relationship, that's what it is. But it's not required by any theory, so you don't see it very often. Decision theory is primarily focused on coming up with your best option, which you get by choosing your most preferred option. Oftentimes, as I said, making utility representation allows you to pick your best option more easily, because you can maximize your utility to find the best option, and we'll discuss that at much more length in later in the part 2 of this lecture course. But you can also ask the question of, let's say I have a whole bunch of rational people, and now rational here means people who have complete and transitive preferences, and reflexive too, but complete and transitive preferences means you're a rational person in the context of economics and political science. It does not mean you have to be selfish or you only care about money or whatever. It just means that you have complete and transitive preferences, and when given the opportunity to pick your optimal choice, you are able to pick your best option given your complete and transitive preferences. It's not too hard for you. Then you're a rational decision maker. The thing is, as was discovered for the 50s and 60s and some 70s, even a group of completely rational decision makers with complete and transitive preferences who could individually tell you what their best option was, when put together, can't always produce good group outcomes. And this is a topic of social choice theory, which is another large area of social science research, in which the goal is to understand how to come to group decisions given a series of individual preferences. Usually the individuals are assumed to be rational in that they have complete and transitive preferences. Turns out that a lot of things we would like to work easily don't work well in the group. So for instance, let's say you have pairwise majority rule, and you have people with these preferences. Sorry about that. Minor, there we go. A is preferred to B is preferred to C. And then someone else has B is preferred to A is preferred to C is preferred to A. And then someone else has C is preferred to A is preferred to B. Each individual can tell you what they would choose. The first person would choose A, the second person B, and the third person C. You might ask, well, what if they just all play this game in pairs, and they basically have little round-robin tournaments, and A is matched against B, majority rule, B against C, and C against A, and whoever gets the most wins, wins. Well, what happens? A beats B from two people. So A beats B. That's majority rule, right? B beats C from two people, the first and the second. So B beats C. C beats A in the second and the third person, so C beats A. But this is exactly the Condorcet triple, the cycle that we had before. A beats B, B beats C, C beats A beats B, and so on forever. So we get no actual majority outcome with these preferences. Each individual is perfectly rational. However, the group comes to a non-transitive decision, a non-rational decision. And this is one of the many issues that social choice raises with respect to preferences, group preferences. And it's not just this. There's all sorts of issues. This is often called majority rule instability because the majority rule can't produce a stable outcome because of this cycle. There are other famous theorems about this. You can get around this cycle by constraining preferences to be of a particular type in which you have an ideal point. Everyone has their own ideal point. You can order them on some line. If you go to 2 dimensions in your preferences, so you assume things are important not just in one dimension, like a left-right dimension, but also, say, in a economic and a social dimension, then that all goes away, and you have, again, real problems with majority rule. There are other problems you can bring up. Arrow's theorem is an extremely famous theorem that tells you cannot come up with a method of aggregating preferences that satisfies these really nice properties. There are other theorems that indicate that you can't expect people to tell the truth in these situations, to actually tell their preferences accurately. So social choice theory, in a sense, is a body of work, and a lot of it indicates how difficult it is to actually come up with group preferences despite having very clear individual preferences. And relations are necessary to understand social choice theory and how to go about looking at these theorems, these famous theorems that have underlied political science and social science for decades now. Relations lie at the bottom of it because relations help you understand preferences, and preferences are the core concept in decision making. Okay. That's all we're going to talk about with respect to relations. Now we'll be moving on to things like sequences and series and limits and so on. Thank you very much.